Good. mgh. Okay, which means you have one object which is small m, and here you have a level, right? Here you have another level. Therefore, you said this is h, right? Therefore, if you said this is 0 height, therefore this height is called h, right? Therefore, the total energy right here at this location is calculated mgh. Now, what's the energy on this level?
0.
0. Why?
Because no height.
Because this one is 0, right? Or you said, no, I don't know where the origin is. I have this height as h1, this height as h2. So what's the total energy here?
It's mgh2.
Okay, mgh2, right? Oh, we don't care where the origin is.
Right.
Probably right here, or you measure the h2 here, right? Or the 0 is here, you measure h2 here. It doesn't matter. Okay, just basically this. Therefore, what's the energy here?
mgh1.
Oh, mgh1. You see, this number can be changed all the time. It depends on where the origin is. And you are the one to set up the origin. You are the boss, right?
Yes.
If you said here is 0, it is 0. If you said here is 0, therefore there's no h1, h2, right? Okay. In another word, if you have a potential energy, this number can be any number. It's not important. It's a random number, has no meaning at all. But if I ask you, what is the potential energy change between these two levels? How do you calculate? For example, you go downward. You go from this level to this level. What's the potential energy change?
mgh2.
It's the final energy subtract initial, right? Therefore, you have mgh1, h1 minus mgh2. Therefore, you see, mg is a common factor, right? Therefore, you have h1 minus h2. And what is h1 minus h2?
h.
It's h, right? If this is larger, therefore it's positive h. If this value is smaller than this, you have negative h. You will have a negative potential energy. But that doesn't matter, right? Energy can be positive, can be negative. Therefore, you see here, that's the real meaning of this energy. This EP is not potential energy, it's a potential energy difference, basically. Only the difference has a meaning. Otherwise, the pure number of potential energy, it means nothing. Because you can change the number by changing the position of the origin, right? Okay, therefore, for potential energy, only the difference makes sense to people. Otherwise, it has no meaning. All right? Okay. Let me remove this and return to here. Now, we want to do another thing which is called electric potential energy. We need a formula similar to this one. Let's see how can we find it. But now we have to change the situation from here to electric. All right, therefore, for gravity, you have an m here. For electric, you have to have what here?
A charge.
This small m is attracted by the Earth, right? And if you said electric potential energy, the particle must be attracted by some kind of force, right? What's the force between charges?
Q.
It's charge.
A charge.
It's Coulomb force, right?
Yeah.
Coulomb force. Therefore, you have to have a charge instead of mass for electric. You just label it differently. This is M attracted, this is Q attracted. From this point of view, they are the same, right? They are all applied by a force on it. All right. And this difference, we call it height. If you have two charges like that, you move this charge from here to here, for example. Oh, here, let me see, this is the positive direction. Okay, this one you can also assign a positive direction. This charge, due to the force, is moved from here to here. Therefore, this distance, you cannot call it height. Because for electric force, gravitational force is too small. We already proved, right? It's too small, can be completely ignored. Therefore, that's not height, it just traveled a distance, right? Okay, can we call it x? All right. Now, we are ready to find the potential energy for electric. So dear EP, well, look at those three parameters. This is M, the mass. The equivalent thing in electric field is called Q, right? Okay. Therefore, we replace M by Q. They are equivalent. And what's this? Gravitational acceleration, right? Is this a constant?
Yes.
Yes, on the Earth, yes. If you are not going too high, this is a constant. And what's the meaning of 9.8 meters per second squared?
The force of gravity attracts you to the surface of the Earth.
To how the Earth is attracting you.
Yes.
Right.
Or how strong the attracting force is. The larger the M is, the larger the force is, right? In other words, this G is how strong the gravitational field is. Right?
Right.
If you go to the moon, the G value is only 1/6 of the Earth. Therefore, right there, the gravitational field is much, much smaller. But on the Earth, it's strong. Therefore, the so-called G is the field strength. Do you have a field strength between charges? If you have a charge here, it will generate a field, which is called electric field. But here it's called gravitational field, right? Therefore, from this point of view, we have to have a field right here for electric potential. Do you have electric field?
Yes.
Oh yes, what is it? What's the symbol?
Electric.
F.
Oh, yeah. I wasn't expecting that. So it's just energy? Is that what you're
It's
saying?
just E.
Is that E?
E.
Or is that that
Yeah.
I thing?
That's the definition.
Yeah.
You have a charge, generate a field, you put a point charge or a test charge over here. This is the source, right? You put this one over here to see how large the force is on this test charge.
Right.
But this field, the field over here doesn't depend on how large this is. It depends on how large this is, right?
Right.
Therefore, from this equation, the force between those two is KQ null R squared, right?
Yeah.
You divide it by Q null. Therefore, these two cancel. That's the field generated by this source charge. And it depends on the Q only. It has nothing to do with this one. Now, what's this one? This is called test charge. In other words, this is just a detector over here.
Right.
Try to detect how strong the field is over here, right? But finally, you don't have to have it here. That's why you have to remove it. Because this field over here only depends on this source. It doesn't depend on what kind of device you are using here, right? Therefore, that's the field. And that one tells you how strong the electric field is. And this one tells you how strong the gravitational field is.
Okay.
From this point of view, they are similar, right? So what's the equivalent to the H here? See? They are the same thing, okay? X. Therefore, we got the equation for electric potential energy. Again, this energy has no meaning at all unless you assign a zero position, right? If you have a zero position, therefore this one is no longer potential energy, the potential energy change. This is the energy relative to the assigned origin, right? If the origin changed, this number will be changed. This is basically an energy difference. All right. We just do a comparison between these two. We got a formula, but we are not sure this is right. If you do science, that's a good way to do it, but you have to prove this is valid, right? What's this? Think about it. F. See, from this equation, F equals QE, right? Therefore, this combination basically is force. And X is just a distance. You move this charge from here to here. Force times distance is what?
Acceleration, speed.
Force times acceleration. M times A is the force. But the force times distance is defined as...
Wait, say it again. Force times
Just say it.
distance. Force times distance. That's...
Oh my God.
Velocity.
Yeah, is it acceleration or velocity? Because that was my...
I said
Oh
acceleration,
my
that was
God.
wrong.
I was going to say.
See, force, distance,
Newton meters.
work. Yes, I did the work here.
That's right.
What's the unit of work?
Newton meters.
Newton meter is called
Joules.
Oh,
joules. What's the unit of joules? What's the meaning of joules?
it's the energy to...
Energy
Yeah.
unit is called joules, right? Therefore, this is the joules. This combination also gives you joules. Yeah, that's a good equation, right?
Very good.
You should have known.
See? Therefore, this is good. This is a good equation. That's it. Potential energy. Okay?
Don't judge us by that question.
Please.
But just one thing, we try to get used to it, okay? Because in Ohm's law, by Coulomb's law, we use R to present distance, right? We don't use X, right? To be consistent, therefore, the best way is you just use R instead of X, okay? That's our convention in electronics. Distance is labeled by R, okay? Therefore, everything becomes very clear. I want to keep going to see what I can get. Okay, the Q is just a charge, right? E is the field. Who generated that field? We don't know. Probably there is a large charge here, which is Q. Who generated this field, right? Not over here, basically over here. This source charge generates a field at here. Therefore, for example, attract this one. Therefore, this one goes this way, right? The distance is R, okay? Therefore, how to express this field? We suppose this is a point charge. What's the equation for the electric field of a point charge?
Q over R squared.
Yes, we know that before, right? And R is here, the distance there. And I see, a good thing happened, huh?
Yes, very
One R cancel. Therefore, you have K, small q, capital Q over R. Okay, I just give a square on this one. That's what we get finally. Electric potential energy can be calculated by using this formula. And this is a special situation. We assume this is the source, this is the charge. And in the general situation,